As I mentioned in class, we're going to be using hexadecimal quite a bit to look at addresses and examine memory. If you already know how to convert between binary, decimal, hexadecimal, you can skip this video entirely. If you're a little bit uncertain of it, I'll try to give you a real quick rundown of how to convert between these different number bases. So hopefully this is a quick review. Inside a computer, all information, data, programs, whatever, is stored as a series of binary digits, or bit. A bit can take on the value either 0 or 1, and that's it. And from those bits, we can build larger, more complex structures. So 8 bits comprise a byte, and so when you hear about megabytes, that's basically roughly 1,000,000 bytes. And going above bytes, there's the notion of a word, and any machine will have a native word size. For most of the past couple of decades, the native word size has been 32, but long ago it was 16, and recent machines you'll see that they're 64-bit architectures, which means that 64 bits is their fundamental word size. For most of this class, we're going to assume 32-bit machines just because it's a little more manageable and a little smaller, and we can keep track of it a little bit better. The words in red on this slide are ones that you should actually know what they mean. And if you don't, go back and read the slide again. Now, if we wanted to examine memory, we could look at it as a series of bits, but looking at large numbers of ones and zeros is not entirely satisfying. So traditionally, we use other bases that are both amenable to a binary representation, but somewhat higher level. So we're all comfortable with decimal, and it would be great, except 10 is not a power of 2. And so 10 doesn't pack bits very well. So once upon a time, octal, which is base 8, was a common way to look at numbers. Today, hexadecimal is the common way to look at numbers. And so hexadecimal just means that we're using a base 16 representation. So we have the digits 0 through 9, and then we add A, B, C, D, E, F to give us 16 different values for any numerical position. So binary is base 2. You only have 2 digits, 0 and 1. Decimal, we all know, is base 10. So the way to think about it is that a decimal number has a ones place, and then a tens place, and a hundreds place, because that corresponds to 10 to the 0th power, 10 to the 1st power, and 10 to the 2nd power. Well, binary is exactly the same way. It has positions that correspond to 2 to the 0, 2 to the 1, 2 to the 2, etc. So in a binary digit, the positions are the ones place, the twos, the fours, the eights, and my prediction is by the end of this course, you'll be really, really comfortable with powers of 2 up to at least 4096 and perhaps beyond. So that's binary. And then hexadecimal, or base 16, is the same way. So we have a ones place, 16 to the 0th power. We have a 16s place, which is 16 to the 1st power. And then we have a 256th place, which is 16 to the 2nd power. Let's start with binary. You should be comfortable reading binary numbers up to 255. And ideally, at the end of this slide, you'll know why 255 is sort of a magic number with respect to binary. So it's actually relatively easy. All you need to be able to do is to add up combinations of all the powers of 2. So 1, 2, 4, 8, 16, 32, 64, and 128. And once you know how to do that, I can teach you to count up to 63 on one hand and up to basically 1023 on two hands. So just like with decimal numbers, the least significant digit, or the least significant bit for binary, is on the right. So if you look at the number 123, right, we know that the 3 is in the ones place, and then the 2 really means 2 times 10, and the 1 means 1 times 100. Well, that's exactly how we look at a binary number as well. So we start over at the right, and this means 1, 1. This means no 2's. And that means 1, 4. So 4 plus 1, that number equals 5. That's all there is to it. So let's do a couple of examples here. We have a 1 plus 2 plus 4 plus 8. So I did these in the numbers corresponding to the bits, 8, 4, 2, 1, that equals 15. Similarly, we have just a single 8 here and nothing else, so that's 8. We add the 8 and the 1, we get 9. And now we've got a bigger number. So here's our ones place, 2, 4, 8's place, 16, 32, 64, and 128. So when we add, all those numbers up, we get, I hope, 201. So pause the video for just a moment and convert each of these binary numbers into their decimal value. The first one is that value I thought might look familiar to you, 255. And basically, the way to think about it is if you added one more bit in this number, so if we added a 1 here, the value of that bit would be 256. So all ones before that is 1 less than that, and it's 255. And if you do the addition and add 1 plus 2 plus 4, etc., you'll also get 255. Now there's a couple ways to figure out the next one. You could have just taken the value of these places and added them together. I looked at it and said, well, if I subtract, I know that if I put 4 ones there, that would be equal to 15. And in fact, that gives me the next problem. And so if I just subtract 15 from 255, I get 240. So once you become familiar, you can use tricks to make this stuff easier. This one, I didn't see any easy way to do it, so I added 1 plus 2, 4, 8, plus 16 plus 32. That gave me 48, 50, 51. Similarly for this one, I added 1 plus 1, 2, 4, 16, and 64. So 64 plus 16 plus 4 plus 1, that gives me 80. So that should give me 85. Now, mapping between binary and hex is actually even easier. There's not really any addition or subtraction. It's really just figuring out what bits correspond to what hexadecimal digits. So let's start by going from binary to hexadecimal. What we're going to do is, starting at the right side, we're going to group the bits into sets of 4, and each of those sets of 4 bits is going to correspond to one hex digit. So if we have this string here, I'm going to start on the right-hand side, and I show you the blue boxes, but what I'm really doing is I'm starting here and I'm saying there's 4 bits. 1, 2, 3, 4, here's 4 more. 1, 2, 3, 4, here's 4 more. 1, 2, 3, 4, and 1, 2, 3, 4. If I didn't have around 4, I would just add zeros to give me a set of 4. Given these sets of 4 bits, I can now map each of those into a hex digit. So 0101 is equal to 5, because I've got a 1 in the ones place and the 4 place. Here, all we've got is a 1 in the 4 place, so lo and behold, that is equal to 4. If I look at the next set of 4 bits, 0101, well, I've seen that before, that's equal to 5. Now I have 1101, so that's a 1, nothing in the 2's place, plus a 4 is 5, plus an 8 is 13. So if A equals 10 and B equals 11, C equals 12, then D must equal 13. So that's why that's a D. Finally here I have a 1 in the 8's place and all zeros, so that's an 8. So this binary number corresponds to this hexadecimal number, which we write as 0x, that says hexadecimal 8D545. So when you write hexadecimal numbers, don't forget to preface them with the 0x. That's how we know we're talking about hex. Now that we've gone from binary to hex, it should be pretty obvious how to convert the other way. Each digit in a hexadecimal number corresponds to 4 bits. So turns out that you can start to spell words when you use hexadecimal because you have some letters. And a long time ago, somebody decided that unallocated memory would be initialized to the hexadecimal number dead beef, because that was a very recognizable pattern. So if you were debugging and you saw you had dead beef in memory, you would know that this was memory that was supposed to be free. So that's why I've chosen this number. It is really not making any statement about cows or beef. So if we want to convert this number into binary, we can start at either end. We take each digit and we say D. What is that? That's actually 13, and I know how to write 13 in binary, which is 11101. So that's my D digit. Next, I want to convert E into binary. So, well, that's going to be 14, so I need an 8 plus a 4 is 12 plus a 2, so I get 1110, and that gives me an E. A is equal to 10, so that's going to be an 8 plus a 2. We already did D once, so I'm just going to copy that over. B is equal to 11, so that's got to be an 8 plus a 2 plus a 1. And sure enough, I've got an 8 plus a 2 plus a 1. And I've already done E a couple times, and then finally F is all ones, so 1111. So this hexadecimal number corresponds to this binary string. Sometimes you'll find that you want to convert back and forth between bases, and it gets a little tedious to do all the addition if you really want to convert things into decimal. I find the BC program, which stands for, I think, Basic Calculator, is actually a very, very handy tool to let you convert between bases. So it's an interactive command line tool, and I'll demo it in just a second, but the basic idea is you can set what input base and output base you want. So if you say I base equal 2, that says I'm going to enter numbers in base 2 or binary. And then if you say O base equals 16, then that says that the output base is going to be base 16. Then you can type in a binary string, and it will print out a hexadecimal string. And you can set I base and O base to anything you want. So I'm going to demo that for you in a minute. For small numbers, learn to do those in your head, but if you really need to convert big numbers, BC is a great tool to use. Okay, let's do a little practice with BC. So I fire it up by typing in BC, and if I just type a number, it just types it back to me. If I want to change base, what I do is say, well, I'm going to type in decimal, and I would like it to type back to me, so I would like the output base to be binary. So if I type 5, I get 101. If I type 16, I should get a 1 and 4 zeros, and I do. If I type in 127, what should I get? I should get 7 ones. And if I type in 256, I should get a 1 and a bunch of zeros. 8 of them to be exact. Okay, what if I want to go into base 16 instead of base 2? Well, let's change our output base to 16. And now let's type in 127. And lo and behold, I get 7F, which corresponds to a 7 is 3 ones, and F is 4 ones is 7 ones, and sure enough, that is what I got in binary. So I can type in pretty much any number I want, and it will give me hex digits in return. Now let's say what I want to do is I want to go from binary into hexadecimal. Well, now that means that my input base is going to be 2. So I'm going to type in binary. So if I go 01010101, I get 55 in hexadecimal, which is what I would expect. If I type in 1234, I better get an F. Great. If I type in 1010, what do you think I get? That's right, it's an A. Good. Now, let's say I want to go the other way. I want to go from hexadecimal into binary. What I'm actually going to do is I'm going to exit BC, and I'm going to go back in. And the reason is that I've already changed my input base to binary, and you would have to express the changes in the input base, and that gets confusing, so let's just start again. This time I want my output base to be base 2, and my input base to be base 16. My advice, once you've changed the input base, if you're going to change anything again, exit and start over. Otherwise things can get a little confusing. Okay, so now I'm going to enter some hex digits. Oops. Let's make that go away. All right, I'm going to enter some hex digits. And annoyingly, BC only recognizes capital letters instead of small letters. So you do have to use capitals for your hex digits. So I type in 2 Fs and I get 8 ones. If I type in A, B, C, D, I should get 16 bits. The first 4 right? If we look at this, the first 4, 1, 0, 1, 0, is 8 plus 2 is 10. The next 4, 1, 0, 1, 1, is 3 plus 8 is 11. So that was those 4. Now I have 1, 1, 0, 0. So that should be 8 plus 4 is 12. Sure enough, that's a C. And then 1, 1, 0, 1 gives me a D. So this is a really convenient tool that you can use to go back and forth between any number bases you want. I would still make sure that you know the lower numbers and only use this for the higher numbers.